welcome back to our office. Come on in, have a seat. We're going to have some pretty easy day today, and it'll be the beginning of a bunch of lectures on very similar topics. So today we'll talk about numerical differentiation. And you may not think immediately, so what, is this really an exciting topic? Well, the exciting thing about it is that it's basic mathematics. And those of us in science, physics maybe more than other sciences, use mathematics as our language. So in order to do science on the computer, you have to be able to do mathematics on the computer. Why do we do mathematics? Is it because we like to look highfalutin, we like to look really sophisticated and, different from people on the street? The answer is no. It's not because we're smarter. In fact, it's because when you do the mathematics, what would be much harder to explain in words and in pure thought become much easier and more logical. So the reason we do mathematics is it's not only our language, but it makes things much easier. Okay? So today we're going to talk about numerical differentiation. And you can think of this as a topic in its own right, in which case it's a pretty simple topic, it's pretty obvious, it's very easy, you should be able to go through this very quickly. Or you can think of it as a preliminary to our discussion of differential equations, and particularly ordinary differential equations, these ODEs we have up here. Okay, and we'll talk about that next time. In fact, we'll talk about differential equations for a few times and build it up. None of these topics are very hard, but it's nice to build up. So if you know this kind of material already, you can jump ahead. If not, you can listen to it quickly. It should be pretty easy. So why don't we get going? Let's look at the first slide, slide number 2. What you see on slide number 2 here is a problem we're given. So let's say you've gone into a laboratory and you've measured the position of a particle, we're calling it y of t, its height, as a function of time. And we get a bunch of numbers, and that's what we have on the graph here. These dots, be they black or red, are just the positions we've measured. Now in a real experiment, you'd measure lots of little positions very closely spaced, so you get good precise measurements. But here we've spread it out a bit so that it's easy to see. Okay. And what we have as our problem is, given this set of measurements of y as a function of t at fixed spaces, determine the derivative, determine the velocity as a function of time. Now you can think of this as a table of numbers, and you can think we don't have any analytic expression for y of t, so we have to do it numerically. Now the truth is, even if we had sort of a complicated analytic expression, it's often easier and less problematic, less chance for error, to just do a numerical derivative. And so y of t could be measurements, it could be the results of simulation, it could be some complicated expression. And we imagine having it at time 0, time h, time 2h, as if these are uniform step sizes. They don't have to be. If you have a function on the computer, you could be evaluating the function at whatever times are needed. So we'll think of that too. But here h is the step size. Okay? So if we look at equation 1 on the slide, we see the mathematical definition of derivative. Now what is derivative? Well, the word derivative comes from derive, so it's something we derive from a function. In mathematics sense, it's just the difference of the function over some time interval. In terms of the graph here, it would be just the slope of the graph at any one time. Okay? So the mathematical definition of derivative, equation 1 here, says, by definition, the derivative of some function y as a function of t is defined to be the difference in that function at a slightly larger time minus the function at the present time, t, divided by the difference, h. And then we take the limit as h goes to 0. So the calculus aspect of derivative is that we're taking a limit as time goes to infinitesimally small differences. That's fine. That's the mathematical definition. You can't beat that. What happens if we do applied math, if we actually try to evaluate the derivative in equation 1 here on the computer? Well, you know what happens. If you take the difference of two numbers that get arbitrarily close, what will you get? Well, if they are very close, closer than machine precision, you'll get 0 in the numerator. And if they're not, or if they're close and you may just have some round-off error, you'll get round-off error. So if we try to do this on the computer, what would we get? Well, we'd get a number for the derivative that lies someplace between 0 and machine precision. Maybe machine precision divided by h, but in any case, it's just noise. So while it's a good mathematical definition, it's not a very good definition to use on the computer. Okay, so let's look at slide 3 here and say, what could possibly be a better definition? So take a look at slide 3. Look at the pretty picture. The easiest definition of derivative for the computer. It's not a very good one, but it's used all the time, and we'll see just why. The easiest definition of derivative on the computer is known as a forward difference method. Forward difference, obviously it means we'll take the difference as we go forward. So what it shows here on the graph is we'll start at time t, the first red dot, and we'll move forward a distance, h, the time step, and that's the difference. Okay? That's all we'll do. That's all derivatives on the computer are about. They're about the difference in a function over a small interval. So if we look at that difference, we're saying we're moving forward and we're drawing a straight line between those 2 points, and we'll take as the slope of the straight line, the red dashed line here, we'll take that slope as the value for the derivative. Now it doesn't look too bad here for the function we've drawn, except if you say, hey, we really want the derivative up here and the slope's pretty flat, you realize, ooh, it could have errors. But you get away from that by making h small. Okay, so how do we know how good an approximation this is? Almost everything you do in applied mathematics always starts with a Taylor series expansion. You know, that's the basis. Any function, any analytic function anyway, can be expanded in a Taylor series. So in equation 2 here, the first line, we have a Taylor series. We say a function y evaluated at a time slightly, h bigger than the present time, t, is equal to the value of that function at the present time plus some correction, some differences. First you have the time step h times the first derivative plus h squared over 2 times the second derivative, and so forth, h cubed. Okay? So that's the Taylor series. But if we look at equation 2 here, and we're a little clever, we say, wait, we have y prime of t. That's the first derivative. That's what we're trying to evaluate. So we can solve equation 2 for the first derivative, y prime, and if we do that, we get equation 3. Equation 4. Equation 3 says the central difference the forward difference, I take it back. The forward difference approximation for the derivative. The C here means the derivative on the computer. Okay, so C prime, our algorithm, what we would compute as derivative by taking the function at a time t plus h, subtracting the function value at the original time t, dividing by h, that's the definition, is approximately equal to, and now we use the Taylor series, the actual mathematical value of the derivative with a correction term. And the correction term, if you look at it, it's the next term in the Taylor series here, the h squared term, and when we divide by h, we get power h. Yeah, h squared of h is h. So we get minus h over 2 times the second derivative. So this, equation 3 is the approximation. Equation 4 shows you the correction term. So if you look at equation 3, hey, you'd say, that's just what this guy showed us on the last slide. It looks just like the definition of the mathematics for a derivative. What's the big difference? Well, the big difference is we say you do not, I repeat, you do not let h here become infinitesimally small, because on a computer that doesn't work. But we leave h as a finite number and we take that difference. Okay, and that's it. So that's known as a forward difference. You move forward one step, take a difference, divide by h. That's the derivative. So it's the change in y divided by the change in t, in this case time. What's a better method? So let's take a look now at slide number 4, which gives you an example of what we mean by this algorithm to take derivatives. Okay, so what we have here on equation 5 is, that's just our definition. The C here again reminding you, means what we compute as a derivative in the forward difference is just the function at a larger time divided by a function at a smaller time divided by h, the time step. Okay. Okay. Well, let's take as an example as a function that given on equation 6, a simple parabola, just no linear term in t, just a t squared term. So this would be, for example, the distance an object falls if you drop it from rest in a uniform gravitational field. Okay? If you take the analytic derivative, which is exact, of course, of equation 6, we just, derivative of a is 0, derivative of bt squared is 2bt, we get 2bt. That's the exact answer. What do we get as an answer if we try to do this with our algorithm? Well, we see that on equation 8. So if we actually substitute for this function, y of t up here, we evaluate it at time t plus h, and we subtract the value of the function at time t, what we get is 2bt plus bh. And 2bt, as we have up here in equation 7, is in fact the correct answer. H is an error. That's just what we said. This is a method which has an error that's proportional to h. You could say, ooh, but h doesn't have to be a tiny number. It can't be, otherwise we'll have a limit problem. So that's the problem. In order for this to be a good method, we have to make h small enough so that the error here is not very large. But we can't make it too small or we get garbage out. So it may not be a good algorithm, but it has one thing going in its favor. Not only is it simple, that's maybe two things then, but all of these are simple, is that we don't need to start with any information other than the initial value, which has to be known. So it's self-starting, as they say. It starts off with the initial value of the function. We know the tabulated value up ahead. This gives us a value of the derivative at time 0, or time t, no steps. So that's what's good. Okay. So now let's look at slide 5 at the improved algorithm known as the central difference. What do we have? Well, we have another pretty picture. The picture here is very nice because it shows exactly what we mean by the central difference algorithm. And it says if we want the derivative at time t here in the middle where the red dot is, you step off on both sides, h over 2 back, h over 2 ahead, so the step size h remains constant, and then you just connect those 2 points together with a straight line. And that's our approximation for the slope of the curve at the red dot. And if you look at that, you realize that's not bad at all. That pretty much is just the derivative there. So it is a better approximation. And as h gets smaller, the approximation gets better and better. Okay? So that's the trick. Central difference, we take a difference, centrally located point on both sides. It's still h over 2 on either side. Still h is the step size difference. Mathematically, in terms of an equation, what this approximation here, drawing a central difference line, is represented by equation 9. And it says the derivative, y prime, or dy by dt, is approximately the function at a value half a step ahead minus the value of the function half a step behind, and that's the derivative at time t. That's the trick here. For time t, we go ahead and symmetrically behind, and then we divide by h to get the d by dt, to get the dt part in the derivative. Okay. How good an approximation is this? Well, again, we check by using a Taylor series. And I'll spare you here the pain of actually doing all the algebra on the board, but I suggest you try to do this at home on a piece of paper. It's very simple, and it'll be confusing otherwise with just the words. As I said, math is easier than the words. But all we have to do is evaluate a Taylor expansion for our function y at time t plus h over 2, another Taylor expansion of our function at time t minus h over 2, and then as it says in equation 9, we take the difference. Okay? And if we look at equation 9 here, what is going to happen? Well, if you take the difference, and these series have even and odd terms in it, as you know, they even, odd, it alternates. Any term that's even, evaluated t minus h over 2 is going to have the same value as it has when it's evaluated t plus h over 2. So all even derivatives up above here will cancel. So all even derivatives cancel, and we're only left with odd derivatives in the Taylor expansion. The first odd derivative is the one we want for y prime. The next odd derivative would be y cubed. So the approximation, as we see here in equation 10, The computer approximation for the derivative using the central difference is approximately the first order term, the y prime term, and then we skip to a third order derivative. And normally that would have an h cubed with it, but we divide by h, so it has an h squared. Simple. So the error, rather than going like h, which is what we had for the forward difference, goes like h squared. A higher order power, smaller function, with no more work. We still just evaluate the function in two places. Okay, so this is good. This is why it pays always to be clever. It's almost always better to be clever, use a better algorithm than it is to try to let the computer do more work, because there's less error here. So if we in fact try to evaluate this algorithm in equation 9, the central difference, for our parabolic function, we'd get the right answer right off the bat. So it's good to order h squared, and since this derivative here is 2t, there is no linear term coming in, it gives us the exact answer. Okay, so let's try this. So let's look at equation 6 and say, how do we really, let's look at slide 6 and say, how do we assess algorithms in general and these two algorithms in particular? Well, the first thing I tell you to do here on slide 6 is to read the book. It's always a good idea to read the book because it's a different viewpoint, different language, and we can go through the algebra steps much more easily than having a flash by here. But the idea is the simple one we spoke about before. When we speak about how good an algorithm is, it's always a balance. If we keep making the step sizes smaller and smaller, we then get better answers in a mathematical sense. But when you make the step sizes smaller on a computer, in a numerical sense, you let round-off error accumulate for a longer period of time, and at some point when the round-off error is equal to the approximation or the algorithmic error, that's the best you can do. And that's when you quit. So we ask here, how do we judge? Well, we know for the derivative we're trying to approximate is always delta y divided by delta t. Delta y, if we push it to the limit, is something like machine precision. And delta t is h, the step size. So this is always going to be what the algorithmic error is like when we're done. And if we set that equal to the error that we have just derived now for the algorithm, okay, so this is going to be what our round-off error is like. We have the algorithmic error in terms of the Taylor series. We can actually determine the value of h that gives us the best answer. So let me say that in other words. What we're trying to do is to say for each approximation, the forward difference, the FD, or the central difference, the CD, we want to determine what value of h, the step size, gives you the best approximation. And we do that by setting the round-off error, which here we're saying in equation 11 is always going to be something like machine precision divided by the step size. We set that round-off error equal to the algorithmic error, which is either going to be a term like proportional to h for the forward difference or proportional to h squared for the central difference. Okay? So when you do that, you get equation 12. And equation 12 is interesting but because it seems backwards. It says that if you're doing a forward difference approximation, you have to use a value of h, which is about 5 times 10 to minus 8th, which is a pretty small number. It's better than single precision. It's already double precision. You have to go to that. Whereas if you were trying to do a central difference algorithm, which I said is a better algorithm, then you can use a value of h which is approximately 1,000 times larger. So this seems backwards. The better algorithm means that h is 1,000 times larger. That's right, because h is larger, but if we look back at equation 11 at the error, which is what we end up with, it's always divided by h. So by using a larger value of h, which is 1,000 times larger, you get an error which is 1,000 times smaller. So here we say, not only do you work only 1,000th as hard, you get an answer which is better by a factor of 1,000. And that's what good algorithms are always about. It's not just that you don't make the poor computer work so hard, it's that you don't have to work as long, and therefore you don't get as much round-off error accumulating. Okay, you'll probably need to read this again, work through it before you understand it, because Sounds just backwards, but it's a good example. So let's look now here again on slide 6 at the bottom and say, you've gone far enough. It's time for you to try out these two methods. And actually in the textbook, I give you a third method known as the extrapolated difference method. So that's, again, a method which starts with the Taylor series and says, what if I evaluate the derivative at another point? Can I make yet another term in the series vanish? And the answer is yes, you can. But then you get more complicated. So in practice, I never do anything but central difference or forward difference. It's usually good enough. Okay? So here's the exercise. So roll up your sleeves, take a break, and let's go into the lab and try out these simple functions. Mind you, you can go in the lab. These are so simple, you can just do them on a hand calculator at home or with your computer at home as well. They just take the difference and try it out. So we have 6 steps here for you to try out. The first one says, just take some simple functions whose analytic answers you know, but the method works just as well with known or unknown functions, functions with known unknown derivatives, cosine x and exponential of x, evaluate them at point 1, 1, and 10, fine, and find their derivatives at those points. Compare, of course, to the analytic. Use the forward, central, and extrapolated difference rules, that's fine, and print out your answers and the relative errors as functions of h. And the relative error means the analytic minus the numeric divided by the analytic. Take absolute values so they're always a positive number, because we don't care which is bigger or smaller. That's what we mean by the relative error. Keep doing this till this, and keep making your step size smaller and smaller until you get to a step size which is just about machine precision. So that's the most reasonable small value of h you could use. It should already have been too small for some approximations and still needed for others. You'll see. So for number 5 here, actually make a plot of the logarithm to base 10 of the relative error epsilon versus the step size. So this log base 10 of the relative error, recall, should be the number of significant figures, number of decimal places in your answer. So if you can get, you take a guess. Do you get 6, 7, do you get 10, 11 decimal places of precision? That's pretty good. That'll tell you immediately, and for what h value you get it. And then up here, equation 11 and 12, we've estimated what h value should be. Don't take my word for anything I say. Check it out on the computer. That's what's fun about this, and that's why it's an experimental science after all in its simulated way. Okay, so compare the answers we have on the computer, and then look from the shape of your curves, from the behavior of the curves, where algorithmic error seems to be dominant, or approximation error, and where round-off error seems to be coming in, and if there's some noise indicating round-off error. So go to the lab and do that, and then you can come back and we'll start talking about the next subject. Okay, so the next subject will be on second derivatives, and that's here on 7. So I'll wait a second while you come back from the lab. Okay, so now let's talk a little bit about second derivatives. And physically you can say, okay, we started off with that particle whose trajectory we measured, and then we asked you to calculate the velocity at all the times. Okay, you do that by taking the first derivative. Now we're saying, well, we want to know what the force on that particle is. Maybe the particle's a rocket ship, and we want to know what the force on the people inside of that rocket ship is like. Well, that means we need to take an acceleration, which means we need to compute a second derivative of the position. So do we have to go through all of this again for the second derivative? Well, the answer is no. Actually, the second derivative is, we've done all the hard work. You just take the first derivative of a first derivative, and you have a second derivative. That sounds complicated. So let's look what we're saying. We're saying on equation 13 here, f prime, we started off with the first derivative, central difference, f of x plus h over 2 minus f of x minus h over 2 divided by h. Okay? Notice I changed from time to x, and that's because it's just a variable. It's just a dummy variable. It's just the independent variable. Could be t, could be x, could be anything. Okay? So here we called it x, just to remind you. It's just a dummy variable. So the first thing we have to do is follow the turquoise line and say, first we have to evaluate the function f of x plus h over 2 and make that the first derivative. So we just want to take the second derivative to be the central difference of the first derivatives. So we have it there. We need to evaluate the first derivative at x plus h over 2, subtract from that our approximation for the first derivative at x minus h over 2, which is what we have on equation 14. And that's it. Okay? So if we actually do the substitution here, we substitute for x plus h over 2. Remember what we do. We move half a step forward and half a step back. So x plus h over 2 when we go forward becomes half a step x plus h. When we go back h over 2, we get minus f of x. And likewise, we're subtracting. There's the minus sign. So we have to subtract from x minus h over 2 something half a step forward, which will give us x, which is right there. And then subtract half a step back from h over 2, which gives us x minus h. So some purists will say equation 15 here is the best approximation for the second derivative. Other people will say, hey, you dummy, look at it. We have f of x appearing twice. Why don't we combine it, in which case we get 16, which is much neater looking, simpler to remember. And it says the second derivative is just the function itself, evaluated step h ahead, plus step h back, minus 2 times the central difference value. All divided by h squared, because it's a second derivative. It's like d squared f by dx squared. And the reason the purists like equation 15 better is they say, well, in equation 16, when we add two numbers together, we get a big number, and we subtract another big number from it, so we're taking small differences of big numbers. But in equation 15, we never let the number get that big because we take a difference here, we take another difference, and then we do the subtraction. So part of your exercise for sure is when you take this in the lab, try out the second derivative of those functions we just looked at, cosine x, because you know what the answer is, it's cosine x. Try that out. You can compare both methods here, 15 and 16. In practice, I've hardly ever seen any difference that's significant, but give it a try, see what the purists are being so pure about. Again, start with a small value of h, and then let it get to machine precision. Okay, so now go back to the lab, try out second derivatives as well. And then you can come back here and we'll talk about how to apply this to differential equations. Hope to see you soon. Bye-bye.